Hello there, Mr. Sutton here, bringing you the AB Calculus 6-2 Extra Practice number 6 solutions on separable differential equations. On this problem, we just need to find the general solution to this differential equation. To get started, we're going to have to separate our variables because the output variable, y, is in the differential equation. So to do this, let's multiply both sides by 3y squared to get it with the dy. And then we'll multiply both sides by dx to get it on the other side of the equation. At this point, it's time to take antiderivatives. So on the left side, this is going to be y cubed. And on the right side, going left to right, we have, let's see, bumps up to a 4. Dividing by 4, we have just x to the 4th. And this will be x to the 3rd. And then plus x. And then don't forget plus c. Now, since this is just the general solution we're looking for, we don't have to plug in an initial condition or anything. We just have to isolate y, which we can do by taking the cube root of both sides. And now we just have the cube root of, well, everything that was over there before. So let's just pick the right answer out of the multiple choice here. It looks like it's going to be choice B, where the plus c is included under the radical. For this multiple choice question, we want the general solution to the differential equation here. So because I have a y in the differential equation, I have to separate my variables first. Let me start by multiplying both sides by 2 cosine of 2y. That'll give me 2 cosine 2y dy on the left side. And then I'll multiply the dx to be over with the 8e to the 4x. Now I can take the antiderivative on each side. On the left side, I'm going to have to use the chain rule, or the reverse chain rule, really. So this is going to be, let's see here, 2 sine of 2y divided by the inner derivative of 2. So that just ends up being sine of 2y. And then over on the right side, we have 8e to the 4x divided by that inner derivative of 4. So that's going to be 2e to the 4x plus c. And at this point, looking at the answer choices, it looks like we just need to get the c all by itself on one side, which I can do by just subtracting 2e to the 4x from both sides. And is that one of the answer choices? Sure is, choice C. On this problem, we want the general solution to this differential equation, and they're telling us y is greater than 0, which might be important. So because I have a y on the this part of the differential equation, in the differential equation, I should say, that means we have to separate our variables. I can't just take the antiderivative the way things are. So let me start by multiplying both sides by 2y to get it over to be with the dy. And then I'll multiply both sides by dx to get it over with the x's. Now it's time for the antiderivative. On the left side, we've got y squared. On the right side, we've got, let's see, sine of x. And then sine of x antiderivative is negative cosine of x. And don't forget we have a plus constant here, plus c. At this point, to get y by itself, we have to take the square root of both sides. Now, normally we would get a plus or minus square root. However, they told us that y is positive. Therefore, we only have the positive square root to worry about. So this is just going to be positive square root of all the stuff on the right side here, including the plus c. Everything is getting square rooted, which is going to give us answer choice D. On this calculator-based question, we're given y equals f of x is the particular solution to this differential equation, and they're giving us the initial condition f of 1 equals 0. They want to know what f of 2 is. Now, normally you could just figure this out using the fundamental theorem. You could do basically your initial value of 0 plus the integral from 1 to 2 of whatever the derivative was. However, you can't really do that here because you'll notice this derivative has x's and y's in it. Really, the big deal breaker is that it has the output variable in the differential equation. So to do this, we are actually going to have to do our little diffie-q dance and find the particular solution. Specifically, we're going to have to separate our variables to do this because we have that output variable in the differential equation. So I'll start this off by multiplying both sides by e to the y. That'll get it to be with the dy over on the left side. And then I'll multiply both sides by dx, so that's x squared plus 1 all multiplied by dx. Taking my antiderivatives now, on the left side I've got just e to the y. And on the right side we have, let's see, 1/3 x cubed plus x plus c. we need to figure out the c value in order to figure out the particular solution that we're going to plug 2 into later. So to do this, I need to plug my initial condition, 1, 0, into this general solution. So we have e to the y value 0 equals all of this stuff with 1 plugged in for x. So e to the 0 is just 1. We can subtract this 1 over here and cancel that out. So we have a 0, and really all that's left on this side is just a 1/3 plus c. Subtracting that 1/3 gives us negative 1/3 for the c value. And then we can go ahead and plug that back in for c up here. We're almost there. To get y by itself, we have to take the ln of both sides. So doing that, we have y equals ln of, well, pretty much everything on the right side there. And at this point, we need to actually plug 2 in and figure out what this comes out to. So this is the part that I'm going to do on the calculator. To make things a little easier on myself, I've entered this whole ln of 1/3 x cubed function in my calculator under y1 in the y equals. And I'm going to quit out of there now and do alpha trace and pull up y1 from that menu. And I'll just plug 2 in this way. This way I don't have to worry about messing up parentheses or something trying to plug 2 into all these different places. So press enter. Comes out to about 1.466. And that's going to be answer choice B. On this problem, I'm trying to find the solution to this differential equation given an initial condition of 0, -3. Probably the toughest part of this one is getting started. We see that we have an output variable, a y, in the differential equation, which means we know we're going to have to separate variables at some point. But separating variables is kind of tricky on this. To do it, we need to take this 2 and move it over to be with the y. So we'll have negative y plus 2. So that part itself is kind of easy, or 2 minus y, however you want to write it. At this point, we have to divide both sides by 2 minus y. We can't really separate the 2 and the y. We have to do this by dividing by everything. So that's going to give me a dy over 2 minus y equals, and now we just have a 1 left over there. We're going to multiply that by dt to get dt not on the left side. So we have a 1 dt. At this point, I can now take the antiderivative of each side. On the left side, that's going to give me ln of absolute value of 2 minus y divided by the inner derivative of negative 1, so negative ln of absolute value of 2 minus y equals, and using our reverse line rule, this is just going to be 1t plus c. At this point, we have to figure out the c value. To do that, we plug in the initial condition. So I have negative ln of 2 minus the y value, negative 3, so that's like 2 plus 3, I guess, or 2 minus negative 3, equals, we have a t value of 0 that we plugged in that initial condition, so 0 plus c. So back on the left, this is just going to be negative ln of 5, and since there's nothing else on the right except c, we just have c equals negative ln of 5. So we're about to plug that back into this general solution. Before we can do that, though, we have to resolve this absolute value. We can't just leave it there. So to do that, we look at our initial condition again, and we see that if y equals negative 3, then 2 minus y is going to come out positive. The stuff inside the absolute value comes out positive, which means we don't actually need to negate anything to make the absolute value do its job. We can just replace it with a regular parentheses and let the chips fall where they will. So I can rewrite this as negative ln of just normal parentheses, 2 minus y, equals, we have a t, we have a minus ln of 5, and all we have to do at this point is isolate y. So next step, I'll just multiply everything by negative 1. So I have ln of 2 minus y equals, I guess, negative t plus ln of 5. And to get rid of the ln, now I have to raise e to both sides. That gives me 2 minus y on the left side, and this is going to be e to the negative t plus ln of 5 on the right. We could split that up, though, into e to the negative t times e to the ln of 5. Since e to the ln of 5 is just 5, I can write that whole right side as just 5e to the negative t. So I skipped a couple steps in getting there. And now I just have to subtract 2 from both sides and multiply everything by negative 1. So when the dust settles, then, I have 2 minus 5e to the negative t, because normally we would have had 5e to the negative t minus 2, but then you multiply by negative 1 and those get reversed. So that ends up giving us, let's see here, answer choice C. For this free response problem, the population of a virus in a host can be modeled by the function A, satisfying this differential equation here, t minus 1/5 A. And let's see, A is measured in millions of virus cells, T is measured in days between time 5 and 10. It's kind of interesting. And they're telling us at time 5 there's 10 million cells of this virus in the host, because everyone loves hearing about viruses. Okay, so our first task on this one is writing an equation for the line tangent to the graph of A at time 5, and then using that to approximate the number of virus cells at time 7. So let's start with our tangent line equation. This is going to have the general format of L of x equals f of a plus f prime of a times x minus a. Applying it to this problem, we're going to have a of 5, because that's kind of our launching off point, our point of tangency, plus a prime of 5 times t minus 5. So now we have to fill in some specific values here. A of 5, we actually were given that. They said at time 5 there's 10 million cells, so we can just put 10 in for that. And then a prime of 5, well, for that we're going to have to go to this differential equation and actually take the derivative, or use the derivative. We already have the derivative. So if I'm plugging 5 into this equation here, I'm plugging in 5 for t, and for a I have to plug in the a value when t is 5. So that a value again was 10. So I'm doing 5 minus 1/5 of 10 in that differential equation. And then that's going to come out to, let's see, 5 minus 2, which is 3. So when the dust settles then, I've got 10 plus 3 times t minus 5. And to actually figure out the number of viruses at time 7, I can say a of 7 is approximately equal to 10 plus 3 times 7 minus 5. And let's see, if you actually want to simplify this, this is going to be 3 times 2, which is 6, plus 10 is 16. So that's going to be 16 million virus cells. For this part of the problem, they want us to show that a of t equals negative 25 plus 5t plus all that stuff satisfies this differential equation that they gave us with initial condition a of 5 equals 10. So there's two ways you could do this. One would be to actually solve this differential equation with the initial condition and show that it equals what they set up here. A faster way to do it would be to simply plug in 5 for t and see if this gives you 10 back, and also take the derivative of this thing and plug it into this equation and see if you get the same thing on both sides. So I'm going to go with the just plug it in and check approach. Since we don't actually have to solve the differential equation, we just have to verify that this is the solution. So let's plug in 5 to start with here. A of 5, that's going to be negative 25 plus 5 times 5 plus 10 times e to the negative 5 over 5 plus 1, all that stuff. And I put 5 in red. That's what the 5 that I actually plugged in there. So this was, let's see, negative 25 plus 25 cancels out. And this is going to be, let's see, 10e to the, well, this is just negative 1 plus 1. So that's 10e to the 0. So 25's cancel. We just have a 10 left over. And that's exactly what we wanted, because they said that a of 5 should equal 10. So we've shown that we have the initial condition at least working for the function that they proposed as their particular solution. Let's make sure the differential equation works out, though. So to do this, I'm going to basically come up with both sides of this differential equation using the a of t that they gave me. And then I'm going to just show that those two things give me the same expression. Let's start with dA over dt. That's just the derivative of a of t. So taking that derivative, that's going to give me, let's see, 5 plus, we're going to have 10e to the something multiplied by the derivative of the something, which is just negative 1/5. So we're using the chain rule on this second portion here. And 10 times negative 1/5 is negative 2. So we end up with 5 minus 2 e to the negative t over 5 plus 1. So this is the expression that we want to try and match now with this t minus 1/5 a stuff. Now what are we plugging into this t minus 1/5 a business here? We're just going to plug in this a function for a. So I'm just going to write, instead of t minus 1/5 a, I'm going to write t minus 1/5 negative 25 plus 5t and all the rest of it. And I'm just going to try to make sure this comes out to 5 minus e to the, or 5 minus 2e to all that stuff. So distributing this negative 1/5, we end up with t plus 5. And then we have a minus t. And then this is going to be minus 2e to the negative t over 5 plus 1. Positive and negative t are going to cancel. So in the end, we just end up with 5 minus 2e to the negative t over 5 plus 1. So this is exactly what we got when we did dA over dt up here. Since I've shown that the two halves of this equation come out the same, using a of t as my base, that shows that a of t is the particular solution to our differential equation. So I guess QED, we're done with this one. For the last part of this one, this part's kind of a beast. It doesn't even require the original part of the problem. It's, for all intents and purposes, kind of an independent problem. They're saying the host receives an antiviral medication. Amount of medication in the host is modeled by the m function, which satisfies this differential equation here. And let's see, m is in milligrams, t is in days, whatever. K is a positive constant. If the amount of medication in the host is 30 milligrams at time 0 and 15 milligrams at time 3, so we're being given two different data points here, we want to know m of t in terms of t. So translation, solve this differential equation. And we have an initial condition of, I guess you could say 0, 30, and we also have this other point of 3, 15 that we might use as well. All right, so solving this, one thing that we're going to have to do is going to be to separate our variables, because you notice that we have the output variable m in the differential equation. So I'm going to divide both sides by m. That gives me a dm over m on the left side. And I'm going to multiply both sides by dt to get that away from the m's. So on the right side, we're going to have negative 1/2 dt over t plus k. At this point, I can take the antiderivative on both sides. Now, when I do this, you're going to notice that we end up with a lot of ln's. Just to save me a little bit of time resolving things down the road, it's worth noting that m and k are both going to be positive numbers, greater than 0. You can't have 0 milligrams on this stuff. You also can't have, they said the k was a positive constant. Now, t could be 0 because they said t equals 0 days, but time can't be negative. So m is positive, t is at least 0, and k is positive. So that means that we don't have to worry about taking the ln of a negative number down here with this m. We also know that t plus k has to be a positive number, so we don't have to worry about taking the ln of a negative if we have a t plus k inside the ln. So when I do my antiderivative, I can write ln of m with no absolute value. Over on the right side, I can write negative 1/2 ln of just t plus k, also with no absolute value, plus c. All right, so at this point, let me go ahead and solve for c. To do that, I'm going to plug in, let's see here, our initial condition was 0 days for t and 30 milligrams. So I have ln of 30. And over here, this is going to be negative 1/2 ln of 0 plus k plus c. Now, kind of annoying because we have this k sort of hanging around. And unfortunately, at this point, there's really no way to get rid of it. It's just a constant, though, so we're just going to kind of take it along for the ride here. So we can say then that c equals ln of 30 plus 1/2 ln of k. And that's going to have to be as good as it gets. And if you want to, you can pop that 1/2 in to make this k to the 1/2 power. So if you really wanted to, you could combine all of this by multiplying the stuff inside here, and then this would be ln of 30 times the square root of k, which looks a little bit nicer. So I think we can live with this a little bit. We're not quite done, though, because we're still going to have to find the value of k. But let's go ahead now and plug c back in. And remember before I said we already resolved the absolute values by saying that m, t, and k were all 0 or greater than 0. So we don't have to worry about that. We can just plug in ln of 30 radical k for c over here. At this point, though, we still need to figure out what k equals, and then after that, we still need to isolate m. So we still have a long to-do list here. But let's start figuring out k. So kind of on the road to doing this, I'm going to simplify a little bit. I do notice that every single one of these terms has an ln, and I sure would like to get rid of those. To do that, though, I need to combine the ln's on the right side here. So I'm going to do a couple of things. This negative 1/2 power can be popped in to give me the reciprocal of t plus k, and also put it inside a square root. So this is really ln of 1 over the square root of t plus k. And I can merge these ln's by multiplying the things inside. So when all is said and done, I end up with ln of 30 radical k in the numerator and radical t plus k in the denominator. And one other little step I can do, since I have an ln on both sides, I can raise e to both sides, and now I just have m equals 30 radical k over t plus k. Okay, so this is a better situation than what we had up here. At some point, though, I do need to solve for k, so can't put it off any longer. Let's go ahead and figure out how to do that. So for that, we're going to use this other piece of information they gave us. They said we have 15 milligrams, m is 15, when t equals 3. So I'm going to plug in 15 for m and 3 for t, and I'm just going to solve for k. So to do this, let me first divide both sides by 30. That gives me 1/2 on the left side. And the nice thing about doing that also is that I've got essentially one big radical on the right side. We could think of this as just the square root of k over 3 plus k if we wanted to move those radicals in together. So I can just square both sides now to get rid of those radicals. And I end up with 1/4 equals k over 3 plus k. Well, this is kind of like you saw back in geometry. You can just cross multiply here. We have 3 plus k equals 4k. And then, let's see here, subtract k from both sides. We have 3k equals 3, so then k equals 1. But hold on, we're not done. We still have not actually solved for m. So let's just go back to this one right here, where we had m equals 30 radical k over radical t plus k, because this one almost has m fully expressed in terms of t. We just have to take the extra step of actually plugging 1 in for k in this form of the equation up here. So if we do that, we can write this as just m equals 30 over radical t plus 1. And this is as good as it's going to get.